got this guy. So we're working on integration by parts, and we'll be doing it today, and we'll finish it tomorrow. And essentially what it does is it allows us to find the integral of two things multiplied, as we know. And it's a formula, f capital G, take away the integral of f dash capital G dx. And like I said yesterday, it is a formula in one sense. There is a formula here that you use, but it's also a process, because very often what you have to do is that you have to do it at least once, but sometimes even twice or three times. So you have to repeat the process, just like I think an analogy I probably gave was like L'Hopital. Sometimes you have to do L'Hopital twice or even three times to get the answer. What I've got here might not seem that important, but it is. This is the equivalent to the product rule in differentiation, right? This is how you integrate two things that are multiplied. It's not exactly a one-for-one correspondence, but it's close enough. But in Calc 1, when you differentiated two things multiplied, it really didn't matter which one you called f and which one you called g, because you got the exact same answer. There wasn't any algebra issues. There are issues with integration by parts. It is important that you choose the correct guy to be f of x and the other one to be g of x. I tend to focus on which one is f of x, because whatever's left is g of x. And so here are the three most common situations, and then there's a fourth one that I've not written down, but I'll tell you about it. In situation one, if you ever get a polynomial times somebody, you know, like this, or x cubed sine x, that kind of thing, then make the polynomial your f of x. It's a bit like rule. Do you know when we did U sub, didn't we have various rules about how you figured out who the U sub was? This is kind of the equivalent going on here. How you pick your f of x. So if it's a polynomial times somebody, pick the polynomial. If it's a single function on its own, call f of x, whatever that function is, and call g of x 1. So essentially, we make this a product by calling it log x times 1. So it's a bit of a workaround, but it works very successfully, so we use it. If you ever have a function, and here we've got two, obviously, but if you've got one function that you cannot integrate, then you choose that one for f of x. So in this question here, it says x cubed log x. So typically, if you're using rule 1, you'd pick the polynomial. But this gets overtaken by this rule. We cannot integrate log x. The integral of log x is not anything at all. It's not 1 over x. That's what you get when you differentiate it. So you have to be aware that, you know, sometimes this rule doesn't work and you have to use situation 3. You have to use the thing that cannot be integrated. You have to make that your f of x. Now, the fourth one, the reason I've not written it is it's kind of hard to say, and each time I say it, it's slightly different. There are going to be situations where none of these rules work, right? None of them apply, right? They're just one-off integrations that you're going to do integration by parts with. And you've got typically something times something, right? So who do you pick for your f of x and your g of x? Well, one method is just bite the bullet and pick one. And if it works, if you've picked the right one, then this integral here will be nicer looking than the original, right? It will simplify the question down. And if you pick the wrong one, you'll know it, because this guy here will be ridiculously ugly. It'll be even uglier than the one you started with. And normally you see that, okay, that one didn't work, switch places, guys. So the fourth situation is, if none of these rules apply, if the thing you've got doesn't really fall into any of these categories, you can either just randomly pick who you want to be f of x and see if it works, or you can try and pick f of x if you can predict it, so that you know this is going to be simpler. And if you choose the right one, it should be simpler. So what I've got here is a big selection of functions that we are going to be using integration by parts on. And the first thing that we're going to do is get some practice on who is the f of x and who is the g of x. Right, in this question here, x cosine of 4x, who should you pick as your f of x?
X.
Great. That would come under what? Situation 1, right? What about this question? Let's just do who you pick as f of x, because g of x is whatever's left, right? Who would you pick as your, I guess I should call it f of t. Who should you call your f of t here?
Just t.
T. Let's change it. Let's pretend it was t cubed. Wouldn't you pick t cubed? Might be the same though. What about this one then? Who would your f of x be this time?
X minus pi.
Okay. Now every single one of them is essentially situation 1, isn't it? This one is do not pick f of w equals w. It doesn't work. So who do you choose?
Would it be the natural log of w?
Yes. Now that comes under the category of situation 3. Log of w, which would probably be the g in most questions, right? You cannot integrate the log of w. If you can't integrate me, make me the f. Right. What are you going to do in this next one? Who should you choose as your f of x when it's a log x over an x squared?
The natural log.
Yeah, very similar to the one above. How about x squared plus x cosine x? Who should you choose as your f of x this time?
Would it be x squared plus x?
It would be. So we're back to situation 1 again now. What about just log x on its own? Who do you pick this time? I'm surprised I haven't got an answer yet.
The natural log of x.
Yes. Doesn't that count as situation 2? In fact, doesn't this one count as situation 2? And doesn't this one count as situation 2? If ever you only have a single function to integrate, inverse, cosine, log, whatever it is, that's the guy that's going to be. In this case, it's probably worthwhile telling you who the g of x is going to be. It's going to be 1, because you're pretending in a way that this is log x times 1, thingy times 1, thingy times 1, right? So we're artificially making a product by calling it the thing times 1. Okay, last one of this, and then we'll start doing some questions. Who would you choose to be your f of x in this last one?
Natural log.
Natural log, didn't you? Too late now, call it x. Are we getting a little bit more comfortable about the who you pick for f of x, who you pick for g of x, right? None of these ones here didn't fall into one of these categories, right? But I'll show you an example of a situation that doesn't quite match later on. Hopefully today, but definitely by tomorrow. So no particular reason. Let's do this one. This is a version of question 7. So it's going to be the integral of x squared plus 4x cosine of x dx. And we've already talked about one, so I hope that you would be comfortable with your f and your g. You feel good with those two guys? Right. Now, once they get a little bit complicated, I actually kind of like to do this as my working. So not only do I say who f and g is, I actually find out what their derivative or integral is. Are you okay about the integral of cosine being positive sine? Right. And now we have our guy. And it's going to be f of x, capital G, take away the integral of the derivative of f, capital G of x, dx. And at this point, it's kind of plug and chug. This guy times this guy. Take away the integral of this guy times that guy. Would you agree that this integral needs to be done with an integration by parts? So I'll just set it up. The f of x is going to be 2x add 4. The g of x is going to be sine x. The derivative of f is just going to be the number 2. And the integral of a sine is a negative cosine. And so this answer here, just move it over a little bit, is going to be x squared plus 4x sine x. Then it's going to be take away, because we've got this guy. And then I'm going to do an f of x, capital G of x, take away the integral of a derivative, capital G of x, dx. Okay, 2x plus 4, followed by a multiplied by a negative cosine x, take away 2 times negative cosine x dx. Can you see that there's a lot of things inside things going on here? So I'm going to spend a little bit of time trying to make things a little bit cleaner. Okay, you're going to subtract that guy, but this guy is already negative. So the net effect is I now have a positive term. This one's going to be even messier. You're going to subtract something that's negative, which is already negative inside. So when you put those all together, are you happy about why this last one ends up being a negative? Are you comfortable with just keeping track of the subtractives, subtractive, and negative, and so on? We're good? Now, at this point, we're finished, aren't we? Because we can get this integral the usual way and we can stop. So our answer is going to be x squared plus 4x sine x plus 2x plus 4 cosine x. And if you integrate 2 cosines, you get positive 2 sines, so you're going to subtract them and then stick a plus c. So the integral of this is that. Are we good? You comfortable with that one? You remember to shout out if I screw up with a sign or something, because I have been known to do that. Let's do one more of those, and then I'll do something for situation 2. So I'm going to do another one from situation 1. I just need to find it. Yeah, why not? This one will do. So pi take away x, cosine of pi x dx. Now, it's situation one, so I'm going to just pick the polynomial as f, and whatever's left is the g. And I'm going to differentiate this guy, and it's a bit messy, but it's okay. It's -1. The integral of this guy, remember we talked about the linear shortcut method that allows us to do sine 2x, cosine 4x, that kind of thing. It can work with cosine pi x as well. If you integrate the cosine of pi x, you will get the sine, positive sine, of pi x. But what else will you get? What goes here?
1 over pi.
I think I heard it very faintly.
1 over pi.
Agreed? Right. Now, if you don't see that, can you do a little scratch paper and do a u sub u equals pi x? You know, 3 minutes later, you'll get the answer. So everything is ready to go. So this fella is going to be f of x, capital G of x, take away the integral of f dashed of x, capital G of x, dx. I'll bring over here for room. And so it's going to be pi minus x times capital G, which is the stuff, take away -1 times the stuff. And I'll try and simplify this, but I'm not really sure there's an awful lot I can do. Guess it looks like that. And this becomes plus. And we got that guy. Well, we're pretty much finished because this we can integrate. So with all this again to do. Now, if you integrate a sine, you get a negative cosine. If you integrate a sine pi x, you get a negative cosine pi x times a 1 over pi, which you've already got one, so you've now got that much, plus c. Are we comfortable with the answer? Pretty ugly answer, but it's the answer. If we did not have integration by parts, do you think you could have guessed the antiderivative of this and come up with that? Because if you could, you're a better person than I. I don't think there's any obvious way to guess. I mean, in fact, you might be thinking, where on earth did that pi square come from? Well, we know where it came from, right? But if you didn't have this working, would you even have thought about putting a pi squared on the bottom or whatever? I doubt it. So there's not, you need this technique, right? There's not a way of, just doing it by trial and error. So let's look at a single function on its own sum, and I'm going to do 2 of them. So I'll do this one first. And then I'll do a really ugly one after that. In this situation, when there's only one function, you make the f of x that function, and you make the g of x 1. Right, that's what you do if there's only one function. Now, we know the derivative of this guy is 1 over x, and we know how to integrate the number 1. We get x. Are we okay with that? Why we chose the f and g and what f dashed and capital G look like. So we should be able to just put the package together, and hopefully it'll come out nice. It's at times like this, I wish I had one of those wooden things that you could just go kadunk and write down that formula. Wouldn't it just, actually, I wish you could do it Have you noticed that you end up repeating yourself over and over again because it's the same as the top line, just one extra little bit different each time, and it does get quite laborious. I don't know how to avoid that. So f of x is the natural log of x times an x. Take away 1 over x times an x. I like the x's at the front, so that's that tidied up. Oh, would you look at that? Didn't that come out nice? And in this case, if you want to integrate a 1, you get an x, so that's negative x, and then plus c, and boom, done. So we now know what the integral of log x is. Interesting. If I had the time, which we don't, can you trust me that if you differentiate that, you get this guy? Now, you might get this guy with a 1 added on, or a plus, a minus 1. That's just an arbitrary constant that disappeared. I wouldn't worry too about it. I'm pretty sure it just gives you that. Okay. So let's look at an ugly one of those. And I know it's called inverse cosine, but for the life of me, I can't find it right now. It's just so I can tell you what number it is. Oh, there we are. It's question 8. This is another example, right, of situation 2. So the function is going to be the inverse cosine of x, and the other function is going to be 1. And this is going to get some cobwebs moving. What is the derivative of the inverse cosine of x? God, that could have been 6 months ago since you've seen that guy. What's the derivative of the inverse cosine of x?
Is it -1 over square root of 1 minus x squared?
Are you reading that out, or are you just got a good memory, Kira?
I'm reading it off of my integral table. I have my integral notes and I just looked at the other column.
Right, well, it's not a surprise. I think we're comfortable. That's correct, right? You just take it for granted it is. So now we can put the package together. I'm a great believer. I know we've only just started, we're in week 5, but the more of these darn things you can memorize, derivatives and integrals, it's just going to make your thought process smoother. You know, if you do something, you have to pause, find a piece of paper, figure out what it is, and then come back. Don't you lose that continuity in thought? And it just is, you know, put some time into trying to memorize these darn things. They just make your life go quicker. They do. So it's going to be f of x, capital G of x. Take away the derivative, capital G of x, which is that's going to probably move them over for room. F of x is inverse cosine times an x. Nothing too special. And the derivative, yuck, this guy, times an x. So let's just tidy it up for a second. X, inverse cosine of x. Those two cancel out to get a plus. And now we're here. And you might be thinking, oh, it's just one of those questions where you do integration by parts again and it'll come out okay. But trust me, you don't do integration of parts on this question. I'm going to put it over here on its own. And so I want you to have an open mind about what techniques you know to find integrals. And I've already said to you, the technique of integration by parts is not going to work. So what other techniques have you got that you could use to get that guy's integral?
Would we just use a U sub?
Correct. You know, it's okay to have U subs in integration by parts questions, right? There's no law that forbids you having two techniques used to get an answer, right? And I know that's, you know how when you do questions, it's everybody's a U sub and then everybody's this and then everybody's that. And I think that gives you a false impression that only one method gets you the answer. And this is a good example of that. What U sub would you use?
1
1 minus x squared.
Combination. Agreed. 1 minus x squared. And let's go through the process then. So you differentiate with respect to x and you get negative 2x. You do the crossover. You divide both sides by negative 2x to isolate the dx. So this fella becomes x over the square root of u times negative 1 over 2x du. And the x's cancel out. And I'm going to make this negative a half. And I'm going to write this down like that. Because to me, it's just more natural. And we're here. So where are we off to now? I want to integrate this, but I have to do stuff to make it possible.
You have to turn it into u to the power of negative 1/2.
Can you remember week 1? Didn't we do things like that? So what we've got here, it started life off as a special integration by parts. Then a piece of the answer turned into a U sub. That U sub turned into a special version of the power rule. Agreed? Lots of different things happening just to solve this one question. So it's add 1 to the power, which is positive a half. Divide by the new power. Oh, technically, I guess you get negative 1. But isn't that negative the square root of u? And doesn't that become negative the square root of 1 minus x squared? So we now know that this answer is that. So we're finished. It's x inverse cosine of x's minus the square root of 1 minus x squared plus a c. Can you see how this question is a really good example of a good math question? Doesn't it involve you having, you know, lots of different things? Integration by parts, U subs, and a little bit of fractional work. Good question, I like it. Let's move on and show you an example of situation 3 then. We're going to give you a question where one of the functions cannot be integrated, and that's going to be the function that you should choose as your f of x. So the one we're going to pick is version of question 10, which is that guy. I'm looking at that question. Typically, wouldn't you make f of t the power, right? T4. And then you'd make this the g. But you cannot integrate log t, right? And so if you cannot integrate it, make that your f. And whoever's left becomes your g. Are you comfortable about how we had to break rule 1 so we could use rule 3? Now, the derivative of this guy is not particularly onerous. It's just 1 over t. And the integral of this guy is really just a power rule, so nothing too special about that. So we should be able to put the package together. hopefully get something nice out of it. So it's going to be f of t, or capital G, take away the integral of f dashed of t, capital G. And what do we got? We have a log t times a 1/5 t to the 5. Take away a 1 over t times a 1/5 t to the 5. Okay, this guy is really just cosmetic. One over t times 1/5 t to the 5. Would you agree that that can simplify a little bit? Would you agree that t on the bottom cancels one of the powers? Are we comfortable with where that 1/5 t to the 4 came from? Are we good? Right. So this here is just a power rule. So here it goes. Add 1 to the power is 5. Divide by the new 5. 2 5s together give me 1/25, and we're finished. Are we good? Let's go hunting for another one of those. Oh, it is what it is. No, that one doesn't really qualify as a type 2. I've done that one. I can't find another one. Evidently, they're few and far between. Yeah, okay. I'll make one up then. Maybe I just haven't been paying attention. So we want a question where you have to pick one but can't pick the other. So I need to find something that doesn't integrate. The log x definitely doesn't integrate. It's not as easy as you would think. I'm going to try and do this one with integration by parts, but you got to remember I've just made it up right now. So if it doesn't work, I might have to go back and say, I'll make that x cubed or something to make it work. So just a warning off the top. Forget it. I know it's not going to work, even if I change it. Okay. I give up. I am not going to be able to find you another one of these because I can't see one in the thing. That's probably why there's so few of them. They're hard to make up. That's fine. So let's pick a strange one then instead. There's a strange one. Agreed. It's a weird looking one. Who are you going to pick as f of x? Got to pick somebody. So who are you going to pick?
Would you pick just x?
Yes. Now, differentiate that guy, you get 1. Okay, this one's going to require some thought. If you find the antiderivative, if you integrate 5 to the x, you do get 5 to the x, but don't you get something else? What else do you get when you integrate 5 to the power of x, or anything to the power of x, essentially? What goes in the bottom?
Natural log of 5.
Yeah. See, things would go a lot quicker if we had that one, right? But it's such a rare one, isn't it? We've only seen it a couple of times. Right, all the pieces are ready. And where are we going? And f of x is that guy times capital G of x. Take away the derivative times that guy. Really not much you can do to that guy. Guess maybe write it like that. Do you know we can integrate this, right? We don't need to do anything too special. It's really just a version of 5 to the x. So let's see what we get. If you integrate 5 to the x, you get 5 to the x divided by the log of 5. Since there's already a log of 5 here, you square it. And we're finished. Are we okay with that one? Here's a really ugly one with some extra added on. All the ones we've been doing so far are indefinite integrals. This one has limits of integration. What I suggest you do when you've got definite integrals like this is treat them exactly the way you normally do. In other words, don't worry about these limits of integrations. Get to here, but instead of the plus c, once you get to here, take out the plus c, put a big bracket, and then just say x equals 0 to x equals 2. Right. So that would be my suggestion. Now, this one is a stinker, but it has to be, right? Get the best till last. This is, by the way, this is our last question, even although we've 10 minutes to go. So be prepared for some weird stuff. Okay, we need to begin with picking our f and our g. I think that's pretty straightforward. Who is f of x going to be?
Inverse tan 1 over x.
Doesn't that qualify a situation 2? Now, that guy's x, not a problem with that. This fella here, we have some issues. So I'm going to do it over here. We are going to have to differentiate that guy. I'm going to rewrite him in a slightly different version, like that. Do you recognize that is going to be a chain rule? Now, when you do the derivative of an inverse tan, isn't the answer 1 over 1 plus x squared? But in this case, isn't the x going to be 1 over x, or x to the negative 1? So it's going to be 1 over 1 plus the thing squared. And then don't you follow by finding the derivative of the thing? You see, the reason I wrote it this way is to make differentiating it a little bit different, right? A little bit easier. So if you want to find the derivative of this, it's 1 plus the thing squared times the derivative of the thing. And if you differentiate this guy, can you trust me you get that? Now, that means I have this fella and this fella. Are you with me so far? Would it surprise you? I don't think, hopefully it doesn't. Would it surprise you that you need to do a fair amount of style points on this, or else you're going to get into trouble? Right. You know, I'm not going to leave it like that. Would you agree that is not a good place to be? So we have to figure out what that would look like if it looked prettier, right? What I call style points. You want to throw any ideas out? It's an algebra issue.
Negative 1 over 1 plus x to the negative 4th.
No, not that one. I like the thought you're thinking. That's. I thought you were about to do that. So let's do that. Oh, you might think, well, God, you've made it worse looking, not better. Do you know there's a trick you can use with fractions? Especially fractions that have fractions in them, by multiplying by a special version of 1. You agree? So where are you going? What am I going to multiply top and bottom by?
X squared.
Now, what that gets me is a negative x squared over an x squared plus 1. Would you agree that that's at least prettier than what we had before? And, you know, that's as good as it can be. So I will live with that. I'm going to have to be quick here, or I may not even get this finished. So it's the integral of the inverse tan of 1 over x. So it's going to be f of x, capital G of x, plus integral of f dashed of x, capital G of x, dx. And f of x is the inverse tan, 1 over x. Capital G of x is x. The derivative of f is that ugly guy.
Would it be 1 over the?
Oh, sorry.
It would be 1 over x squared
Yes.
times 1 plus x squared.
Yeah, that's a minus 1 on the top. I'm glad you caught that. There's an x squared times that negative 1. Right. So it is going to be negative 1 over x squared plus 1 times an x dx. So that's where we are right now. Where are we off to next? Right. How am I going to deal with this guy? x over x squared plus 1. How are we going to deal with him?
U sub.
Correct. Who's the u sub going to be?
X squared plus 1.
Hey, it's just the second question today where we ended up with a u sub, didn't we? So if you differentiate with respect to x, you get 2x. And you do the crossover. It's actually very like the last one. And then you divide both sides by 2x to isolate the x. So it becomes x over u times 1 over 2x du. And that becomes 1/2 of 1 over u du. And okay, what's the integral of 1 over u?
Natural log of u.
So we are looking at 1/2 natural log of u, but won't that become 1/2 the natural log of x squared plus 1? Are you all happy with that? So this fella here is now take away 1/2 the natural log of x squared plus 1. Now, if it had been an indefinite integral, wouldn't I just do plus c and call it done? But since it has a 1 and a root 3, what you do instead is you do, you know, the boundaries, right? X equals 1, x equals 3. So you're going to have to plug in some numbers, and it's going to be root 3, the inverse tan of 1 over root 3, take away 1/2 the natural log. Well, root 3 is 3 when you square it, and add 1 gets you 4. That's the first guy. Take away 1 times the inverse tan of 1, so that's just inverse tan of 1. And this is minus 1/2 the log of 2. So we've got this guy, this guy, this guy. Well, let's just write them down one more line. Root 3 inverse tan of 1 over root 3. Take away 1/2 natural log of 2. Natural log of 4, sorry. And take away the inverse tan of 1. And take away a negative, add 1/2 the log of 2. Now, we do not want decimals, which means we have to figure out what on earth this looks like as an exact value. Let's take some of these guys here and here and see if we can do anything about them. If I take, I'll do it in a side piece of paper, I think. If I take negative 1/2 the log of 4, and I try and combine it with 1/2 the log of 2, couldn't I pull out 1/2 as a common factor and have negative log 4 plus log 2? If I rearrange the order, wouldn't it be log 2 take away log 4? And wouldn't that get me 2 divided by 4? And wouldn't that get me 1/2 the log of 1/2? So I managed to combine them. Agreed? Or negative 1/2 log 2, if you like that, but both are correct. So we got that bit done, right? So we have 1/2 the natural log of 1/2. Would you agree that the inverse tan of 1 in radians is pi upon 4? It's what angle has a tangent to 1, and that's pi upon 4. You might have a problem with 1 over the inverse tan of 1 over root 3. Does anybody know what the inverse tan of 1 over root 3 is before I show you?
Over 6.
That is very interesting, yes. I like that. Oh. Let's show you. Kind of cheap, but it works. Make sure you're in degrees to make this happen. Inverse tan of 1 divided by the square root of 3. and you get 30 degrees. And just like you said, isn't 30 degrees pi over 6? Because it's always in radians. So it's root 3 pi over 6. And what's going on here? There's a plus going on here. That's a pretty ugly answer, agreed. And it did actually take us just 10 minutes, a little bit over. So last name and bye-bye. I'll see you tomorrow. And we'll get to finish off the rest of these guys. So if you have a question, I guess you can hang about. Otherwise, I'll see you tomorrow.
Bye. Have a good day.
You too.